Here's a scenario I've seen more than once. A project team calculates their required sample size. They estimate the coefficient of variation at 18%, run the Cochran formula, get n equals 15 samples per stratum. They collect 15 samples. The VVB reviews the monitoring report. The achieved precision is plus or minus 22%, more than double the required 10%. The monitoring event is invalid. They need to go back to the field, collect more samples, and rerun the lab analysis. That's a six-figure problem from a miscalculation that takes 10 minutes to avoid. This video covers how to calculate sample size correctly for VM0042 projects, the Cochran formula, where to get your CV estimate, and how to distribute samples across strata using name and allocation. The required sample size for estimating a mean with a specified precision is N0 equals Z times CV divided by E, all squared. Z is the Z-score for your confidence level. CV is the coefficient of variation of SOC stocks within the stratum. E is the maximum acceptable relative error. VM0042 requires 90% confidence, Z equals 1.645, and plus or minus 10% precision. E equals 0.10. Example, CV equals 35%. N0 equals 1.645 times 0.35 divided by 0.10, all squared. That's 5.76 squared, which equals 33.2. Round up to 34. That's the minimum number of samples required for that stratum to achieve 10% precision at 90% confidence. If your stratum contains a finite and known number of sampling units, say 120 possible 30-meter pixels, apply the finite population correction. N equals N0 divided by 1 plus N0 minus 1 over N. With N0 equals 34 and N equals 120. 34 divided by 1 plus 33 over 120 equals 34 divided by 1.275, which is 26.7, rounded up to 27. The correction reduces your required samples when the population is small relative to N0. For large project areas at 30-meter resolution, the number of pixels is typically in the thousands or tens of thousands, and the correction is usually negligible. Less than one sample difference. Apply it when you know N exactly and when N0 exceeds about 5% of N. Two things to get right before plugging into the formula. First, use the CV of SOC stocks, not SOC concentration. Stocks incorporate bulk density variability, so stock CV is always higher, typically 10 to 20 percentage points higher. This is not a minor technicality. In the scenario from the hook of this video, the project team used a concentration CV of 18%, which gave them N equals 9. The true stock CV was closer to 30%, which requires 25 samples. They sampled 15 and failed the precision check. Always compute CV from SOC stock values, not raw concentration readings from the lab report. Second, use CV from pilot samples that span the full stratum, not just the accessible or convenient part of the project area. This is a subtler mistake, but it has the same consequence. Accessible parts of a project area, near roads, near farm buildings, tend to be flatter, more uniformly managed, and less variable. If your pilot samples are concentrated there, your estimated CV will be too low, your calculated N will be too small, and you'll fail the precision check at monitoring. Pilot sample locations must be randomly placed within the stratum and must cover the full spatial extent, including high variability zones. A minimum of 10 to 15 pilot samples per stratum gives a reliable enough CV estimate to use in the Cochran formula. If you haven't done pilot sampling yet, use Table 5.4 from the PDF guide as your reference. Homogeneous, silty cropland with flat terrain, 20 to 30%. Mixed cropland with some topographic variation, 30 to 45%. Grassland or pasture, 45 to 70%. Smallholder patchwork landscape, 55 to 80%. These are ranges from published literature and project experience. When you don't have pilot data, use the upper end of the range for your landscape type. It's better to oversample than to undersample. If your data exists, but it's only from the baseline survey, You measured SOC at baseline, and you now want to estimate the monitoring period sample size. Use the baseline CV from your pilot plots as a proxy. The spatial structure of SOC doesn't change dramatically in 5 years. Let me show the toolkit implementation. The sample chart size entre table function prints a planning lookup table, useful for estimating sample needs before you have pilot data. Rows are CV values, columns are precision targets. At CV equals 50% and plus or minus 10% precision. 68 samples. That's the planning baseline for a mixed landscape without stratification. This is the number from Video 4's opening hook. After stratification reduces effective CV to 25%, you'd need around 17 samples per stratum. This table is a quick planning reference. Once you have pilot data and actual stratum CVs, you calculate N per stratum directly with the Cochran NN function. Now calculate per stratum N from pilot CV values. Pilot Touch CV is a list with one CV value per stratum, estimated from baseline sampling or pilot surveys. We call Cochran.N for each stratum with the same precision and confidence targets. Stratum 0, CV 22%, 12 samples required. Stratum 1, CV 35%, 34 samples required. Stratum 2, CV 38%, 37 samples required. Total, 83 samples across all strata. These are the minimums. In practice, you typically add a buffer of 10 to 20% to account for samples that fail quality control, access problems in the field, or CV estimates that turn out to be slightly low. Build the buffer into your field plan, not into the formula output. Now, the compliance check. The VM0042 data compliance check function takes the number of samples you plan to collect and the CV for that stratum. It returns two pass-fail flags. VM0042.pass, true, meets 90% confidence at plus or minus 10%. ICVCM pass, false, does not meet 95% confidence. Shortfall, ICVCM, 8. Need 8 more samples to qualify for the ICVVCM Core Carbon Principles label. This distinction matters if you're targeting a carbon rating from Verra or B0. They effectively require the ICVCM standard. Run this check before finalizing your sampling design. If you're targeting a premium buyer who requires ICVCM grade verification, design to the 95% threshold from the start. It's far cheaper to add 8 samples during the design phase than to go back to the field after a failed audit. Once you have the per stratum N values and the total sample budget, you need to decide how to distribute samples across strata. Naaman. Optimal allocation is the standard approach. Each stratum's share of the total sample is proportional to its area times its standard deviation. Larger strata get more samples because they cover more of the project. More variable strata also get more samples because they need more observations to characterize accurately. This is different from simple proportional allocation, which weights by area only and ignores variability differences. When strata have similar standard deviations, Naaman and proportional give similar results. When one stratum is substantially more variable than others, Naaman can be 30 to 50% more efficient. The Naaman allocate function takes the total N, the area of each stratum, the standard deviation of SOC stocks in each stratum from pilot sampling, and the stratum names. The weight mu-EEX sigma column is area times standard deviation. Higher weight means more samples allocated. Stratum 1 has the highest weight despite being the smallest stratum, because it has the highest standard deviation. Stratum 0 is largest by area, but has the lowest variability, so it gets fewer samples than proportional allocation would give. The comparison column shows what proportional allocation would assign. 48 samples to stratum 0, which is too many, and only 20 to stratum 2, which may not be enough. Naaman does a better job distributing the budget where it matters most. The compare allocations function quantifies how much Naaman outperforms proportional allocation for your specific data set. The SE ratio is 0.91, and the equivalent N gain is 10. meaning Neyman allocation achieves the same standard error as proportional allocation using 10 fewer samples. Or equivalently, with the same number of samples, Neyman gives you a lower standard error. For this dataset, that's a modest gain because the standard deviations across strata are in a similar range. In more heterogeneous landscapes, or when one stratum is much more variable than others, the efficiency gain can be 30 to 50%. Always use Neyman allocation. It never performs worse than proportional, and in most real-world cases, it performs meaningfully better. The PDD documentation for sample size is section 8.2. 4 elements are required. First, the Cochran formula explicitly, not just a citation to Cochran 1977, but the actual formula with the values of Z, CV, and E stated clearly. Second, the per stratum N, both the required minimum and the plan number. These should be in a table with 1 row per stratum. Third, the allocation method, Neyman or proportional, with the formula. The VVB needs to be able to verify your allocation independently. Fourth, the achieved precision at the project level, combining strata by area-weighted combination. This is the headline number, plus or minus X% at 90% confidence. If this number exceeds 10%, your design fails and you need more samples. The toolkit generates the PDD language automatically. The Generate section, 0882 function, takes the pilot CV values, the required N per stratum, the planned N, including any buffer, the allocation result from Neyman allocate, and the precision and confidence targets. The output includes the full Cochran formula with your specific values already substituted in, a per stratum table with all required fields, the Neyman allocation weights shown as a formula, and the achieved precision statement at the project level. The mandatory copy-paste block at the bottom reads, sample sizes were calculated using the Cochran 1977 stratified random sampling formula, required confidence 90%. Z equals 1.645, maximum relative error plus or minus 10%. Neyman optimal allocation applied. Total design sample size, 83 samples. All the blanks are filled in from your actual numbers. The complete sample size workflow is 5 steps. Step 1. Estimate CV per stratum from pilot data using stock CV, or from Table 5.4 using the upper end of the range. Step 2. Calculate required N per stratum using Cochran N. Step 3. Run the compliance check to know whether your design meets VM0042 minimum and whether it meets the ICVCM standard. Do this before you finalize the field plan, not after. Step 4. Allocate the total sample budget across strata using Neyman allocate. Step 5. Generate the PDD documentation automatically with Generate Knowledge section 8.2 and paste it into section 8.2. The entire workflow takes under 30 minutes once you have your stratum CVs. The time-consuming part is getting reliable CV estimates, which is why pilot sampling, done well, is worth the investment. 4 sample size mistakes that cause downstream problems. First, using concentration CV instead of stock CV. Stock CV is always higher. Using concentration CV underestimates N by 10 to 20 or more samples per stratum, and the monitoring event fails the precision check. Second, pilot samples from accessible areas only. This underestimates the true stratum CV and leads to the same result. Third, no buffer on the required N. In practice, some samples fail lab QC, some plots become inaccessible, and some composite samples are damaged in transit. Build a 10 to 20% buffer into your field plan above the Cochran N minimum. Fourth, skipping the compliance check before sampling. If you discover an ICVCM shortfall only after the monitoring event is complete, the cost to fix it is an entire resampling campaign. Run the compliance check during the design phase. 3 things to take away from this video. First, use stock CV, not concentration CV. It's always 10 to 20 percentage points higher. Using concentration CV will leave you with too few samples and a failed precision check. Second, when in doubt about your CV, use the upper end of the Table 5.4 range for your landscape type. Then add a safety margin of 10 to 20% on top of the Cochran output in your field plan. Third, run the compliance check with VM0042 compliance check before finalizing your design. Know whether you meet VM0042 minimum and whether you meet the ICVCM standard before you start sampling, not after. Video 6, Equivalent Soil Mass Correction, covers what to do with the samples once you have them. See you there.